Okay, without any further delay, it is my pleasure and my honor to welcome our keynote speaker for today, Maciej Lewenstein. As a short introduction, Maciej is a graduate of Warsaw University, and he did his PhD in Essen, where he was later a research fellow. And his research path took him to Harvard, to Saclay, the Joint Institute for Laboratory Astrophysics at Boulder, and then to the Center for Theoretical Physics in Warsaw, and to Leibniz University, Hanover. In 2005, he moved to Catalonia, to the Catalan Institute for Research and Advanced Studies, where he's a research professor at the Institute of Photonic Sciences in Castelldefels. His interests include quantum optics, quantum physics, quantum information, attosecond science, and statistical physics. But his other passion is avant-garde music, and he's an acclaimed jazz writer and critic, the author of Polish jazz recordings and beyond. At the Institute of Photonic Sciences, Maciej leads the Quantum Optics Theory Group with 25 members working on the mentioned subjects. Thank you so much for joining us today, and the floor is yours.
Thank you very much, Kasia. It's really a pleasure to be here and to talk to this audience, which I understand is very diverse, and therefore the talk would be kind of general. So the first slide which I show is always with the different agencies and organizations that give the money to finance my research in ICPHO, in Institute of Photonic Sciences in Catalonia, which are from all possible places, from European Research Council, from Catalonia itself, from Spanish Ministry, from United States, from Poland, and also from Germany and things like that. So I collect all this, and this allows me to have a quite a big group. The title of the talk is Brownian Motion Revisited. We will come. So the group is big, like 25 people, 15 PhDs, 10 postdocs. Mostly each PhD has a postdoc as a co-supervisor, and so on and so on. This is a photo of the group just before the lockdown in the Christmas party in 2019. And as Kasia said, she essentially has already went through my CV very quickly, but very nicely. So I'm not going to repeat it. I mean, she has said the most important things. I started my career in Warsaw and ended up in Castelldefels near Barcelona in the Institute for Photonic Sciences as a professor of something which is called Institució Catalana de Recerca y Estudis Avançats, ICREA, which is like a kind of version of French CNRS, but very much limited and elitary, in a sense that they have given maybe 300 permanent position over 20 years in all areas of science in Catalonia. There is a new book actually on jazz, which Kasia also mentioned. Probably next week it will be available in the internet, which is the Amateur's Guide to Avant-Garde, Catalonia, Poland, Portugal, and more. So if somebody is interested in this kind of music, should look for it. Okay, so what I'm going to talk about today is Brownian motion, which is a very well-known phenomenon, which is known in biology, botanics, in physics, in chemistry, and more. And my talk is actually based on the the thesis of one of my very talented students, Gorka Munoz-Gil, who defended in November last year. So the motivation is we look at something which is called random walk. So if you think about the horizontal axis being time and the vertical axis being the position, this walker is making kind of random walk in space as a function of time. And of course, different walkers or at different times, these trajectories look very much differently. So the question is how to understand them. What are the properties of this walk? Is it normal? I will explain what does it mean, or not normal. Is it ergodic? I will also explain what does it mean. Is there a changing in time as the walker walks? So aging, if you wish. The young walkers walk faster than old walkers. There is another property which is called Gaussianity, which I will also explain to you. So, what are the properties of this walk? This is the question. Can we create theoretical models that reproduce such behavior? So, theoreticians introduce millions of acronyms to describe such models like continuous time random walk, fractional Brownian motion, annealed transient time model, whatever. But the main point is what it really is. And what are the best techniques to describe these properties of such a walk, including in the recent years, so important machine learning analysis to classify the models and things like that. So let us go from the beginning to introduce you to Brownian motion and to what I call anomalous Brownian motion or anomalous diffusion. I will be using the word diffusion and Brownian motion more or less with the same meaning. Okay, so Brownian motion or pedesis from the ancient Greek is a random motion of particles suspended in fluid, resulting from their collisions with the fast-moving molecules of the fluid. This was named after botanist Robert Brown, who first described this phenomenon in 1827, looking at the microscope at the pollen of a plant, Clarkia pulchella, in the water. And this is the movie from Wikipedia, so we just show how it, roughly speaking, looks. But of course, in practice, it looks a little different. But anyway, because it's a simulation, what it's showing here are also individual trajectories of this randomly moving particles, which is something that Brown could hardly see, but nowadays we can see it with the modern technology and techniques. So this is Brown, and this is the famous Clarkia pulchella. It's a kind of orchid, I understand, but people who are botanists know better. So if you look at the Brownian motion in the history, typically you talk about Brown, Einstein and Smolokovsky in the beginning of 20th century, and Jean Perrin, a little later, experimentalists who confirmed the theory of these two guys. But the truth is that this is much more richer story. This is really a story of many. And going back to Lucretius, even, who in 60s before Christ has been talking about similar phenomena. And then, yes, we go to Robert Brown, 1826, 27. This is the famous paper of Einstein, and then the famous picture from one of the papers from Jean Perrin. So indeed, Einstein in 95, which was his crucial year for his career, published a paper in which he modeled the motion of the pollen through the equations which now are giving the basis for the so-called theory of diffusion and theory of stochastic processes. This was confirmed, this picture, by Jean Perrin in 1908, and Perrin obtained Nobel Prize in Physics in 1926 for his work on exactly this problem. Einstein, as you probably know, got his Nobel Prize for services to theoretical physics in 1921, where it was for this paper in 1995, for another paper in 1995, which was devoted to photo effect, so some the basis of the quantum theory of light, and for the paper on special relativity. The general relativity and gravitational waves, which Einstein actually did not believe that they can be observed, got never Nobel Prize until very recently when they were really observed. This is Perrin, and this is, of course, Einstein. And this is the paper, the famous paper über die von molekulär-kinetischen Theorie der Wärme geforderte Bewegung von in ruhenden Flüssigkeiten suspendierten Teilchen. Another very important scientist was Polish scientist, in fact, Marian Smolokovsky, who was really giving the pioneering. He pioneered the description of stochastic processes in terms of stochastic equations a la Langevin and others. So he was really one of the pioneers of statistical physics in modern science, and also David Montagnier, actually he died in the mountains. Another one that I want to mention is Kramers, who is a Dutch physicist much later, but he was working a lot on the problem of Brownian motion in the limit of very small mass of Brownian particle. This is Smolokovsky, and this is Hans Kramer. This is Smolokovsky zur kinetischen Theorie der Brownschen Molekularbewegung und der Suspensionen, appeared in the same year as Einstein paper. Kramer is, of course, much later. The language has changed also to English. Brownian motion in the field of force, and the diffusion model of chemical reaction. I mentioned this Kramers because he was talking about the small mass limit of Brownian motion, which is particularly interesting, but this is also related to my mentor and my doctor father, Fritz Haake, who unfortunately died in the end of 2019, who was really one of the world leaders in understanding exactly the stochastic processes of Brownian motion in the limit when the particle that is kicked by the environment is light. It's very, very light, and if you wish, it's overdamped. The damping is very small, damping and friction is very strong. So the typical description of Brownian motion can be included in these three mathematical formulas. I'm not going to give a lot of formulas, but those of you who are trained for it will see it. So the first equation is the equation of probability distribution of Brownian particle being in the position x at time t, and the time derivative of this fulfills the so-called diffusion equation. And this coefficient here on the right-hand side is so-called diffusion coefficient. The solution of this equation can be found analytically, and it's a Gaussian distribution. The particle follows the Gaussian distribution, however, with the width, which is dependent on time. It spreads in time. Indeed, the so-called mean square displacement of the particle as a function of time grows linearly with time and is proportional to this diffusion coefficient. These are the most important characteristics of Brownian motion. Whether this Brownian motion is done in discrete random walk or in the continuously moving particles, these are the most important properties, mathematical properties. Now, typically, this mean square displacement is difficult to calculate. So what the people do They do it in the two manners. They take a position of particle at some time. They calculate, they look at the position of the particle after time delta. They square it and they integrate, average this over all possible initial times. And this you can understand, this is a time average mean square displacement. The other way of calculating or let's say observing this mean square displacement is look at many trajectories of many particles, do the same, look at time t prime and t prime plus delta, and then square and average this thing over all trajectories. So this is ensemble mean square average displacement. In principle, these two quantities do not have to be the same, but the so-called ergodicity property, says that this is the case. The ensemble average is equal to time average. This is very strong property of this Brownian motion, which is really means a lot of things about the independence of individual steps of random walk, of fluctuations and things like that. So I summarize it again. Brownian motion has three main characteristics. Mean square displacement is proportional to time. The probability of the distribution of the particle as a function in space, but as a function of time, is always Gaussian. However, the width of this Gaussian grows linearly in time. And moreover, the motion is ergodic. So average over ensemble of trajectories is the same as ensemble over time. And of course, now when you know what is the Brownian motion, which I call normal diffusion, you know already what is the anomalous diffusion. This is the one which does not fulfill at least one of these properties. So typical thing for anomalous diffusion would be that the mean square displacement grows not like time, but like time to some power. If the power is smaller than one, we call about subdiffusion, because it's slower, so to say, than the standard Brownian motion. If the power is bigger than one, we call it superdiffusion, because it sometimes goes much faster. So the anomalous diffusion refers to the processes that show also non-ergodicity. So the average over ensemble of trajectories of the mean square displacement is not equal to the time average of the mean square displacement for a single trajectory. Non-Gaussianity, which means the probability distribution of the particle at time t at the position x is not Gaussian, it's different from Gaussian. And moreover, there are typically there are correlations between individual steps. Now, in Brownian motion, really, when the walker makes a step in this or that direction, these steps are statistically independent. Here, they can be in the anomalous diffusion, they can be dependent, they can introduce correlations. And finally, the last thing that is also associated often with this anomalous diffusion is aging. So the longer we observe the system starts to change its properties. So for instance, the diffusivity at the beginning can be quite big and everything happens very rapidly, but suddenly at the end, because of aging, diffusivity becomes very small and everything is very slow. Okay. So why do we talk about this anomalous diffusion? Well, we talk about this thing because this is really almost everywhere. So from biology to human behavior to car, traffic, to whatever, chemistry, physics, and so on. So it's really that there's something that is happening everywhere. And of course, the physicists or the, let's say, natural scientists want to be not only physicists, because others are doing equally well, if not better. We try to build the models in which we try to understand where this anomalous diffusion comes from. For the Brownian motion, we know the diffusive behavior comes from the collisions with the environment particles. These collisions are more or less statistically independent, and this is what gives the properties of Brownian motion. But what happens? What gives the what gives the microscopic basis for anomalous diffusion? This is a question which is very intensively studied in the last, let's say, 30, 20 years. So I would like to mention some of the people with whom we have honor and collaborate on this kind of models of anomalous diffusion. This is Giovanni Volpe, who is an experimentalist, but he also does theory, and he works on soft matter physics. So he, for instance, takes kind of polystyrene, let's say, small balls. He puts it in a colloidal suspension, and he looks at the diffusion of the things and things like that. Janek Ver Giovanni is Italian. He finished his PhD at ICFO, but now works in, at that time he was working in Turkey, but now he's in Sweden. Janek Ver is Polish, finished mathematics in Warsaw, and now he's a professor of mathematics in Arizona, or mathematical physics. And they both collaborate exactly on these models of anomalous diffusion, especially concentrating on the situation in which you are in homogeneous medium. So the simplest example that I can that comes to the mind is that you have a medium in which the diffusion constant, which governs the speed of this diffusion or spreading in the Brownian motion, diffusion constant is random, and sometimes it's very big and sometimes it's very small in different regions. And this may lead, if these regions where the diffusion is very small, may lead to sub-diffusive behavior on average, because the particles are trapped, in a sense, in those regions of space where the diffusion is small. Another couple of people that I want to mention are my friends from biophotonics group at ICFO, in particular Maria Garcia Parajo, who is a leader of the biophotonics group, where they do measurements that allow them to track single particles in biological environment. So they can watch the motion, the Brownian motion or anomalous Brownian motion of particles in the biological medium. Carlo Manzo used to be the senior assistant of Maria. Now he has his own independent position and group in the University of Vic near Barcelona. This technique of single particle tracking is amazing because it really allows you to study and characterize the diffusion, anomalous or not anomalous, in a completely new way by looking on individual particles, by comparing, exactly by doing this comparison between the ensemble averages and time averages of the single trajectories and things like that. One of the main things in this biophotonics is that, of course, particles that are biologically active, they do not like to diffuse like Brownian motion. They diffuse with normally, they diffuse anomalously, usually with slower sub-diffusive character, because they have to do something in the biological system. So this is something that you can really study with this technique. And I mean, this is really how it is. I mean, you look with the lasers and things like that, and you can track a single, sometimes you add some marking substances to those particles, but then you can see by looking at the fluorescence from them, you can look single particle, and you can watch the trajectories over very nice resolution in space and very nice resolution in time for quite long time, so quite long trajectories. Okay, the last lesson that I want to say that also gave motivation for us to look at these things is Ralph Metzler, who is a professor in University of Potsdam and absolute leader of the theory of this anomalous diffusion models and things like that. So the development of theoretical description of this kind of anomalous diffusion in the last years was really very impressive, and he was one of the main people who was behind. Okay, so what I just tell you one example of these models that can describe anomalous diffusion. So normally, if you look at the upper line here, imagine that there is a random walk on this line. And this is a discrete random walk, so the walker goes from here to the left with probability 1/2, or to the right with probability 1/2. But typically, this walker does, let's say, 1 step per second or per millisecond, all right? But it's fixed, pam, 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 pam. So continuous time random walk is something different because what happens is that this random walker, yes, it has maybe probability 1/2 to go left and 1/2 to go right, but there is a waiting time distribution that tells this walker how long he or she should wait before making a step. So the times after which he or she takes a step are drawn from are sampled from a distribution. Now, if this distribution has a long tail for very long times, that means that this walker might be stuck here for a very long time before making a step. And this again can lead to the subdiffusive slow anomalous behavior. We, or I should say my Gorka Munoz, very talented student, he has been studying in his thesis various kinds of microscopic models of this continuous time random walk. And namely one which was in the, let's say, crowded environment. So the walker, which is here represented by this black trajectory, walker interacts with other particles which are in the environment. And these particles, well, we call them hunters. So the walker is like prey and other particles are like hunters. So obviously when a hunter catches prey, then the prey slows down because it doesn't move, because maybe even it stops forever because hunter the prize kills him or something like that. But roughly speaking, it was just slowing down. And this kind of mechanism is known in biology. These things happen. So that's one kind of model. Another model that we were studying were this one that I mentioned to you, that we have a disordered diffusion constant. So diffusion can be small in some regions or very big in the other regions. But now we consider a kind of a critical transition in the system in which the regions in which the diffusion constant is small or is big grow and are very, very big. So in particular in this situation, if the particle enters a region of the small diffusion constant, it will stay there for very, 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 very long time, even though doing normal Brownian motion there, but it will stay there very, 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 very long, and therefore on average, the whole diffusion process will be slowed down and it will become anomalous. Another example that we have been studied in recent papers was diffusion in the situation of this kind of compartment. So if you are between the compartment, between the barrier, inside the compartment, which means between the two barriers, you diffuse normally. But then in order to pass the barrier, you need time and you need something. Okay, so again, this can lead to slower diffusion and things like that. Another thing that is maybe very important in those problems and that came to our interest in the recent thing is to try to connect the theory and experiment using more sophisticated analysis of the experimental data. So in a real world, we obtain from the single particle tracking the one single trajectory, which is long, but it's not very long. And we would like, by looking at this trajectory, guess whether there is a model describing it correctly, whatever these acronyms mean. What are the features of this trajectory? Is it normal? Is it anomalous? Is it ergodic? Does it have Gaussian properties? Is there a aging in the thing? And so on. So this is the question, how to go from single particle tracking data to the analysis. And in fact, there are many existing tools like pure statistical approaches, fitting algorithms, and so on, so on, so on. But we recently have developed a method which was based on machine learning. So it's really something like that we were taking experimental trajectories, we were then pre-processing them, putting them into in this case, it was not normal neural network, but some kind of random forest, doesn't matter. It was artificial intelligence system in order to characterize the trajectory concerning which theoretical model describes such trajectory the best, and is the diffusion anomalous or not anomalous. And that was the main idea of this project. So again, which theoretical model better describes the trajectory, which is the exact value of the component, and so on. And this machine learning helps to do it quite efficiently, even for very short trajectory, relatively short trajectory. So the way to do it is to teach, let's say, the network or machine, if you wish, is that you generate trajectories from some models. So for instance, for continuous time random walk, the trajectory could look like that. For fractional quantum with the alpha equal 1, so normal diffusion. For alpha equal 0.7 with subdiffusion, the trajectory could look like that. And for so-called Levy walk, the trajectory would look something like that with very large steps from time to time. Okay, so they are, even when you look at them, they are qualitatively different. So you give many examples to your machine. Machine learns these examples, and then you give the data from the experiment, and the machine is supposed to distinguish what it is. Okay. So as I'm saying, you put the examples, they are labeled, but then so this is how you train. And then at the end, you put just the experimental data and you try to distinguish the trajectories with respect to their characterizations, so anomalous, not anomalous, etc., ergodic, non-ergodic, and with respect to which model could it come from. And we have even, this was very successful, and there are many people who are working on this kind of characterization of anomalous diffusion. So we have even organized, together with this Carlo Manzo, Gorka Munoz, and Giovanni Volpe that I mentioned on the other side, the Anomalous Diffusion Challenge, so kind of contest in the internet of different methods how to recognize the properties of anomalous diffusion single trajectory. So of course the contest when we were generating trajectories from from models, but at the end, the idea is to make the best possible methods of recognizing properties of single trajectories using various methods. The paper about it is prepared for Nature Methods and will be submitted probably next week. Okay, I have not so much time, but let me say another thing that this diffusion and anomalous diffusion is playing a lot of role is in the processes, in even more complex processes in biology, in particular something which is called liquid-liquid phase separation. So normally inside the cell, you have these proteins flowing around. I'm not a biologist, so please don't kill me that if I say something not so precise and rigorous. So there are these proteins flying around, which have certain low density, and some moment they organize themselves into a clusters or condensates of higher density. So these are like membraneless droplets inside the liquid. And this is a process that is very important for cell dynamics, in particular transport regulation. It happens before the division of the cell very often and things like that. And this can be measured with our single particle tracking by looking at the particles that are either outside of these condensates or bubbles or inside, because their diffusion is different in those two environments. So in particular, if you look at the lower panel here, diffusion coefficient measured in experiments of Maria Garcia Parajo and our friends from ICFO, the diffusion coefficient in the cell is usually close, has a peak around 0, so it's small. Now these people add some hormones to the cell in order to stimulate this phase separation process, and then as they follow with addition of this hormone, you see that the distribution of diffusion coefficient becomes bipolar, so there are small diffusions and big, and at the end it's only big. Okay, sorry, no, I did it correctly. No, correct. Yes. Okay. So there are this transition here of the movement of the cell from one situation to another situation. And this is machine learning approach reproduces this kind of things very, very. I was wrong. Yes, sorry. At the beginning, you have big, because this is logarithmic scale, you have big diffusion coefficient, but then when you are in the cluster, you have small diffusion coefficient because you don't diffuse at all. You are trapped in a sense. And the same thing is recovered by the machine learning. And also we have formulated a wonderful model, which is different from other models that have been so far on the market, because essentially takes into account the fact, normally this diffusion limited growth models describe the situation in which the growth of these clusters or aggregated clusters goes to infinity. They fill the whole space at the end. And here this does not happen. So we have some mechanism of unbinding particles from these clusters, and this gives us much better comparison with the experimental data. And I will just, I think, close this talk by showing you the people. So Fritz Haken, my mentor, who really was the first one who taught me about diffusion processes, Giovanni, who is a leader of this classical anomalous diffusion experiments now in Stockholm, we work in our group not only on Brownian motion, but also on quantum Brownian motion. In particular, Pietro Massignan was one of the guys who was working also on quantum. Carlo Manzo, I mentioned, the experimentalist, and Maria Garcia Parajo, single particle tracking. John Lapeyre was essential in the initial phase of this project. Janek Vera, I mentioned, a Polish mathematician from Tucson, Arizona. Juan Toreno Pina is from the biophotonics group of Maria. Senior research assistant Gorka, my PhD student, who is now postdoc, but he is leaving to Innsbruck in the end of the year. And other PhD student more focused on Brownian, quantum Brownian motion, Sampera from Universidad Autónoma, again, quantum Brownian motion student, and so on and so on, postdocs and people who contributed to all this, including several Polish names, as you can see. Przemek Grzybowski, who was a postdoc in my group, but now is in Poznań. He has a docent position. So these are my conclusions. Enjoy physics and beyond. Thank you very much.
Thank you so much for the fascinating talk and for touching on so many elements of the field. I found it particularly fascinating and informative how many areas this can be applied in, and also the ways in which the theoretical and the experimental or the practical field can work together. I see we have a few questions. So Tomek has raised his hand. Maybe we will start for him. Tomek, I will ask you to unmute yourself if you want to ask your question.
Hey, yes, thank you. Great talk, Maciej. My question is, you show multiple scenarios where you can do a simulation of the Brownian or anomalous Brownian motion. I wonder if you can go other way around in a way. Let's say that I have a protein and I know how it behaves in my crowded environment. Can I modify? Do we know how to modify this protein so its diffusion is changed in the crowded environment? So it's maybe diffusing faster or slower depending on my needs. But I wonder if it's possible now to even design a system to behave the way we would like to.
Well, this is, of course, a very fundamental question, because it could have very important applications, obviously, as you can imagine. Because many models of the, let's say, drug delivery on the molecular level are related to controlling the diffusion, exactly. Okay, so of course it would be great. So there are some methods. Unfortunately, I'm not a specialist on that, so I will not answer. I can only say that in the last experiment that I was talking about, this phase separation or creating of these bubbles of more dense liquid inside the liquid, this was stimulated by adding hormones to the molecules. So in a sense, you add some substance, chemical or biochemical, whatever, and you change the properties also. In this case, it was maybe not the character, because the diffusion was the same before and after, but the diffusion constant was changed, or whatever. It was anomalous diffusion. This coefficient, the governing the speed. I think this is how it is. So I think there are such methods, but the people to ask are the people from this kind of single particle groups. They know it better. I'm sorry, but I'm ignorant. Okay. But I think it is possible, and people work very strongly on this, because obviously it would be very, very useful. Okay.
Exactly. Great, thank you.
We have another question in the Q&A from Jonas Słomka. He says, "Thank you for the interesting talk. On a substrate with position-dependent diffusivity, a dilute ensemble of particles would still cover the substrate uniformly. Is that correct?"
Can you repeat, Kasia, but not so fast?
Sure. So on a substrate with a position-dependent diffusivity,
Yes.
Jonas is asking whether a dilute ensemble of particles would still cover the substrate uniformly.
Okay, the question is, I would say that if you wait infinite time, yes, but you never wait. So this is more or less the question. So typically, if you have these regions where the diffusion constant is very slow, and this slow means that it is longer than your observation time, then you will not see this uniformly. Even though in each region the diffusion is normal, still you will see some kind of distribution which is not uniform because you didn't have time to reach it. I think this is the typical thing. It's a little similar to the glasses or spin glasses that you have no time to really reach the thermodynamic or whatever equilibrium. And I think this is very typical in these experiments that they do.
Okay. Jonas says, "Thank you. I have one question from myself, if that's okay, if I can use the fact that I am the chair, because your CV and your career path is hugely impressive, and I think it would be a pity not to ask you a bit about that. I was wondering, especially that we have quite a few people who are quite early on in their careers, usually on our conference. So I guess my question is kind of dual. One is, because you've lived and worked in so many different places, I wonder if you have any reflections on the different cultures of work or the different approaches, for example, on either collaborations or mixing the theory and practice or competition. I don't know, anything around that, or is it that, you know, physics is universal and it kind of feels the same? And then the second part of my question would be whether you have any word of advice for people who are on earlier stages of their career on this.
Okay, so concerning the first thing, I mean, in principle, of course, you answered it saying physics is universal, but the practice again is different. There are different traditions and how should I say? It's not even tradition; it's kind of habits or something like that. So, I mean, let's talk about the one thing. All right. So I worked in Poland. Poland was in the 80s was still communist country, so I had to apply for the passport to go to the other country, the so-called passport służbowy and this kind of things. So it was, of course, something like that. At the same time, if you remember already the end of 80s, you don't probably because you are too young, but in the end of 80s in Poland, the atmosphere political was quite open because the people already knew that it would finish this thing in the end of the 80s. And I would say that I didn't feel very much the centralized kind of control of the science in Poland in the end of the 90s, in the end of 80s, and then in the beginning of the 90s, where I still was in Poland. In contrast, when I moved to France, I immediately think that La République, le président, everything is very centralized, okay? Of course, I was not working at the university or not at the academic institution like Centrum Fizyki Teoretycznej in Poland. I was working in Commissariat à l'Énergie Atomique, which was a huge institution controlling atomic bombs, controlling atomic energy and research. And I was in the civil research, but still, it was much more centralized institution. So one of the reasons I didn't stay too long in France was this, that I couldn't stand this lack of academic freedom, okay? But of course I can say this is not, on the other hand, the thing which in France was much more civilized than in Germany, where I moved after, was the relation to female researchers and things like that. Maybe because of the tradition of Marie Curie Skłodowska, but still, it was much more accepted to have, in Germany, I would say, female working in theoretical physics, everybody would say, this is not, I mean, everybody, I mean, the old German professor, it was very conservative. In the end of the 20th century and beginning of the 20th, maybe it is changing now, but I don't know. And then in this sense, maybe the Catalan situation was the most, how should I say, easy or somehow easygoing. I didn't have this pressures. On the other hand, of course, in Germany, everything is better organized than in science than in some other places. So there are these kind of things, okay? So there are differences in culture, in approach to the things and so on. On the other hand, learning it is very useful. So this is also advice to the young people. They should go to different countries. They should not be afraid of going even to China or something like that and try to learn, because this is extremely intellectually, I think, opening if you work in different environments, in different things. I mean, the United States, I also spend a lot of time. And of course, it is even much more different. Okay? In terms of, for instance, administrative aspects, US is the most easy in comparison to anything in Europe, right? You always have much more bureaucracy here than there. But on the other hand, it's very different. Okay, if you, I don't know, if you don't like American football, then. But this was, so what is my advice? My advice for the young people is, okay, there are two kinds of, I would say, scientists, and both ways are okay. I have been told by this mentioned Fritz Hake, who died, my mentor, after I was doing PhD in so-called quantum optics, and he told me at the end, quantum optics is not a separate discipline of theoretical physics, you have to do other things. So I started to work on statistical physics exactly, and so on and so on. And therefore my scope of interest is extremely broad. He has made me like that I am very, very broad. So in other words, I know something about everything, but of course I'm not a top leader in anomalous diffusion. No, I know something about everything. Whereas there are other types of career in which you know everything about something. And it is also good because this is also necessary and things like that. I enjoy my way because if I'm bored with something, I can do something else. But I wouldn't give it as an advice. This depends on the individual character, I think, and the individual pleasures you can have. It's very important to have pleasure in science. If you don't have pleasure, do something else.
That's really interesting and very valuable perspective. So thank you for sharing it with us. I'm afraid we are slowly behind schedule with the timing, but it has been an absolute pleasure to have you here, and thank you for talking to us about your work. We